Hello and welcome. In this particular video lecture, we are going to continue our discussion on the generic part of reasoning description logic. In the earlier video lecture, we have tried to talk about the concept of semantic consequence. And corollary to that, we have discussed about the equivalence of the T boxes and what we mean by one particular axiom is modeled by a T box and several other things, and we have demonstrated all the concepts that we have discussed, right? So with this we will be now talking about the different reasoning tasks involving the T boxes, right? So basically when we talk about reasoning, the queries they are mostly on the T boxes, and also they can be on the A boxes, right? So it's good to know that what kind of reasoning tasks that are involved in both the cases, right? So the first uh, thing that we like to discuss is the verification of consistency of a T box or a concept, right? So we are trying to define or discuss the verification of consistency. So whenever we have a T box, the T box should be consistent, right? Now, whenever we talk about consistency, we need to answer following thing. So whether the T box has a model, whether the T box has a model. So that means whether there is at least one interpretation which is a model of the given. So we got to find at least one I that is a model of T. So whether we have something like that. Then if we have some at least one such I, then we say that this T box is consistent or this T box has a model. Now what kind of example that we can give where the T box does not have any model? So if we have something like this, so this we make the top class, to be the subclass of the bottom class. It will not have any model. It does not have any model. You cannot think of any model that satisfies this axiom, and if you consider our T box contains only this axiom, then that T box does not have any model and that T box is not consistent, and that is very apparent intuitively, like a top concept can never be a sub concept of a bottom concept, right? So the second thing that we want to answer regarding the consistency, whether a concept is satisfiable, whether a concept is satisfied, right? Now let's define the reverse of this. Reverse of satisfiability is unsatisfiability. So we define a concept, we say that a concept is unsatisfiable if it is empty. It is if it is empty in every model of T, in every model of the T box T. So we consider a T box and consider any concept inside that T box. Now that concept will be unsatisfiable if it does not contain any individual for any given interpretation which is a model of T. In that case, the concept is unsatisfiable, right? So if we try to write it mathematically, how will it look like? So for every I where every I where I is the model of T and uh, the interpretation of C is one empty set. The interpretation of C under the interpretation I is an empty set. So if that is so, this concept C is unsatisfied, right? The reverse part of this, if there exists at least one model of T for which C is non-empty, then that concept is satisfied, right? So let us take an example of a concept which is never satisfied. So if we have something like say C, which is a subclass of say D intersection not D, then this concept is then C is unsatisfied. So basically any concept that is a subclass of the bottom class, so that means the C is empty. So the interpretation of I would be an empty set. In that case, we say that C is unsatisfied, right? Now there are different types of deductions in T boxes. So or the reasoning tasks. So different kinds. We will be talking about different kinds of reasoning tasks in the T box. So T box reasoning types or tasks. So the first task already we have mentioned a little bit is satisfiability. Now we say that a concept C is satisfiable with respect to a T box T if that T box has got at least one interpretation for which the concept is non-empty, right? The thing that we have just mentioned, right? So let us write it down. So a concept C is satisfiable, and of course it should be with respect to a T box T if and only if T has at least one model I. So if I is a model, then you know that this holds I models T, right? Such that the interpretation of C under I is not an empty set. Then this concept is satisfiable. We are defining SAT. We say that a concept C is satisfiable with respect to the T box T if and only if there exists at least one interpretation I such that that interpretation is a model of the T box T and uh, this C, the interpretation of C under I is not an empty set, right? So in that case we say that C is satisfiable under or satisfiable with respect to the T box T, right? Now the second task that we are interested in is subsumption. We already have mentioned this term earlier, but though in a very informal term. So basically this is saying that a concept is included into another concept or a concept is subsumed into another concept, right? So we define the case that a concept C or D subsumes another concept C, and again with respect to a T box, if uh, T can model, or this D, so T is a subclass of D, is a semantic consequence of the T box T, and it should be valid for every model of T. So I, for every model of model, like say I, let us name this model to be I, you have the interpretation of C to be a subclass or subset of the interpretation of D under I. So you see, this particular thing, C subclass of D, was not included earlier in the T box D. This is what we are getting as semantic consequence of the T box T. And when will that happen? So for every interpretation that is a model of this T box T, for that the interpretation of C, which is a set, is a subset, is always a subset of the interpretation set of D, right? So basically we can say that C is subsumed by D under interpretation under T box T, or with respect to T box T, if the T box models something like say C subclass of D, right? So the C subclass of D is a semantic consequence of D. Then we say that C is subsumed by D. So the third task that we are interested in, equivalence, right? And under equivalence, we say that two classes are equivalent, or two classes are equivalent to each other with respect to a T box if and only if T models the equivalent, right? Now finally, the final task that we are interested in, the disjoint, right? So we say that two classes C and D are disjoint with each other with respect to the T box T if and only if the T box T models the statement, the axiom being C intersection D is equivalent to the bottom class. So if this is a semantic consequence of T, then we say C and D are disjoint, right? So these two do not have any individual to be common in the class expressions, right? So if you take intersection, which are disjoint classes, this will bring you to the, or this will get you the bottom class, right? Now the question is, as we have got different tasks, right? So we have got 4 tasks. So should we have different algorithms for different classes? So should we have different algorithms for different tasks? This is the question that we're asking. So my argument would be, if we have a single algorithm to deal with all these tasks, so that is the ideal situation, right? So if we could have a single algorithm to deal with all the tasks. Now, how will that be possible? A single algorithm? If we can somehow translate all the tasks, into a common task, and then write an algorithm for that task, then we don't need to worry about the individual tasks or define algorithms for individual tasks. So for that, we need to check what are the kind of relationships that these different reasoning tasks they have between themselves, right? So if we can see that they can be mapped to a common problem, then we can just write a single algorithm to deal with that problem, and that will in turn deal with different individual tasks. So that is the kind of motivation that we have to draw a relationship between this reasoning tasks. So we'll be discussing a relationship between reasoning tasks. Great. So what are the tasks that we have in hand? So we have satisfiability, or the other version of satisfiability is unsatisfiability. So we have got unsatisfiability. Uh, okay. So we have got unsatisfiability. So this is one task. The second task is subsumption. The third task is disjointness. And the fourth task is equivalence. Now we'll try to see how we can translate the tasks between from one task to another task. So there are certain relationship between these tasks. We'll be leveraging those to find out whether we can write a single algorithms to deal with all the problems. So let us try to. So what do we mean by this unsatisfiability? We are just saying that C is unsatisfiable. And by subsumption, we mean that C is a subclass of D. By disjointness, we mean two classes C and D are disjoint with each other, right? By equivalence, we mean that C is equivalent to D, right? So these are the kind of meanings that we can ascribe to different tasks, right? Now I'll try to see how we can map this unsatisfiability problem to be one subsumption problem. So we have to map this fact that if C is unsatisfiable, then we have to map this in a form like this, right? So let us see how we can do that, right? So we are relating this to, right? So if we can say that C is a subclass of the bottom class, then C becomes unsatisfied. And by that process, we have translated the unsatisfiability problem into one subsumption problem, right? Now let us turn our focus from this translating unsatisfiability to subsumption to translate subsumption to disjointness. So can we do that? So can we rewrite this kind of problem statement into this kind of problem statement, right? So we can say that this, so let us try to draw this. C is a subclass of D. So this is the D representation of the D class, right? And this is the representation of C class, right? And this means that C is a subclass of D, right? Now, does that mean that the complement of D, the complement of D and C, these two do not have any common element? So the complement of D is the other. So if you just take the other part of the universe, so the complement of D will be this part, right? And you see that there is no common element between this complement of D and this C. So we can safely say that these two are disjoint with. So we can map this subsumption to be a disjoint problem, disjointness problem, by saying that the C and not of D are disjoint with each other, right? Now let us try to translate a disjointness problem to an equivalence problem, right? So when we say that two classes are disjoint, if two classes are disjoint, if we take intersection of these two classes, this will become equivalent to the bottom class. And by that mean, we are kind of translating one disjointness problem into an equivalence problem, right? So this is becoming to be an equivalence problem, right? Now, how do we translate an equivalence problem to be one unsatisfiability problem? So this is what we are trying to explore, right? Now, when we say equivalence, so C equivalent with D. So if we say that C is equivalent to D, that means these two hold. So C is a subclass of D and D is a subclass of C, right? And now we can translate this into something like so this can be translated into not of C or D, right? And this, the second part, can also be translated as not of D uh, union or disjunct C, right? Now we are saying that this is unsatisfiable, and in order to put that, we just put a negation before this, and if we try to flatten this out, we just push this negation inward. So this if we push this negation inward, this not C will become C, this union will become intersection, and this D become will this D, and so this negation is over the whole expression, right? And this intersection will become to be union, and this negation D will become D, and this will be intersection and not of C. So we say that this particular statement, this is a concept expression, this concept expression is unsatisfiable. That's how we are transforming one equivalence relation into one unsatisfiability equivalence task, reasoning task, into an unsatisfiability reasoning task. We can also translate the disjointness relation directly to one unsatisfiability problem. So how you can do that? So basically you can say that C intersection D is unsatisfied, right? And you can also translate this subsumption into one unsatisfiability problem, right? So you can say that uh, this C intersection not D is unsatisfied, right? So you see that every task can be mapped to the unsatisfiability task, right? So what we can do, given any reasoning task, first we can translate that into an unsatisfiability task, then try to prove or perform the reasoning. And in that case, you just need to develop an inference algorithm for unsatisfiability problem, and the rest of the things will be followed, right? So the fundamental reasoning task in concerning T box is the concept C is satisfiable or unsatisfiable. So if you can answer unsatisfiable, we can answer also satisfiable. So this is the kind of fundamental reasoning task concerning the T boxes in description. And we will see later that in every reasoning problem, we'll try to first translate that problem into unsatisfiability problem, then we'll be going with our reasoning algorithm, right? Now from this T box reasoning tasks, let us turn our focus into the A box reasoning tasks, right? So we'll be talking about A box reasoning tasks. So the first thing that we need to answer, whether an A box is consistent. Now, by the way, the A box, what does an A box contain? It contains a class membership, it contains a relation membership. Also, in certain logic family, it can contain the negated relation assertions, right? So, these are the kind of three elements that we can have inside an A box, right? Now, when we ask whether an A box is consistent, there we need to check whether the membership that we have assigned for this different individual, whether they are having clash. So if they are having clashes, then our A box will not be consistent, otherwise it will be consistent. So let us start with an example. So if I say that let us check whether A is a member of, say, father, uh, if we say that uh, A is a member of father as well as A is a member of female, right? So considering the fact that we have defined the father definition, father uh, mm, concept properly, then this assignment will not be consistent, right? So these two together does not hold, and consequently it is not consistent, right? So now how long it will happen? So as long, so let's consider other things. So I'll not say that it does not hold, right? So if we do not say anything else before this, then this is perfectly consistent. Now we assert the fact that this father class and the female class is disjoint with each other. We assert this in T box, right? Then this father A intersection female A becomes inconsistent, right? So you see that this T box plays an important role when we talk about the consistency of an A box. So whenever we need to define the consistency of an A box, we should always define that with respect to a T box, right? So the uh, consistency of an A box is always to be checked with respect to our T box. So this is one thing we need to always consider. So you see that if we do not have any T box, right, then this is perfectly consistent, right? But as we have uh, introduced a T box and one axiom like this other female in the T box, then this same thing has become inconsistent, right? Now as we have the model of, we have designated an interpretation I to be the model of a T box, we can also define an interpretation to be a model of a A box, right? And again that should be defined with respect to the T box T, another R T box T, right? So you say that I, so this is what we are kind of defining. I is a model of one an A box A, of course with respect to our T box T, and we represent that with I models A with respect to T, right? That is not a simple model, so it is always with respect to a T box T. If this I satisfies both A uh, and the T box T, right? Now you can think of a particular assertion, and this assertion maybe we can think of an assertion, the alpha, to be a consequence of uh, A with respect to T if A models or A derives alpha given the T box T, right? So when will this happen? So for all interpretation, interpretations, the I where such that this I is a model of A with respect to T and I is also a model of this alpha. If that is so, then we say that this alpha is a consequence of A. This alpha is entailed by A, this A box A. We will be having examples of all these things, right? So let us now talk about different reasoning tasks that are involving this A boxes, right? So we talk about A box reasoning problems, right? So the first reasoning problem that we are interested in as far as the A boxes are concerned is consistency checking. So we say that an A box A is consistent, and again with respect to a T box T, if there is at least one interpretation, there is at least one interpretation I such that this I is a model of A with respect to T box T, and also I is a model of T, right? Now the second problem that we are interested in is in some way this is kind of talking about the satisfied, whether that is there is at least one interpretation for which the A box is satisfied, right? So the second problem in hand is instance check. So in instance checking, we just say that whether alpha is a consequence of a knowledge base or not, right? So basically this alpha, it can be either of these two forms, say CA or RAB, right? And we are basically trying to see whether alpha is a consequence of A with respect to a T box T, right? The third problem that are of great interest is instance retrieval. So here in instance checking, what you are doing, your input is either one individual. So for that you need to check whether this individual is a member of C or not, or uh, the other input can be one relation between A, B, and you have to check whether this is holding true given the A box statements, right? But in instance checking or instance retrieval, we do not have these as inputs, right? So what will be our input? Our input will be either one concept. Our input here would be either a concept or a relation, and you need to check what are the kind of individuals that are belonging to this concept, or what are the kind of properties or pairs that are belonging to this particular rule, right? So this instance retrieval can be defined in concept level or in role level. So we say that given a concept, retrieve all the alphas such that A is so CA is a semantic consequence of B. So I should write say A, I don't say alphas. So all the A's such that this A box derives this CA, right? So let me write it in a very cleaner way. A is a member of C, right? To retrieve all those A's. Now it can also be defined at the role level. So where we are interested to retrieve all the pairs AB such that A and B are individuals and A kind of models are AB, and the input should be given R, right? Now the fourth reasoning task that is involved in this A box reasoning is the realization. Right. So here it is a kind of uh, reverse problem to this instance retrieval, right? So in instance retrieval, we the input were the classes or the roles, and we had to come up with the corresponding individuals that are member of those classes or roles, right? Now here the input will be an individual. So given an individual A, so we will return. So what we can return? We can return the class that it belongs to, right? But we will not be returning any class. So we will be returning only the narrowest classes. Return the narrowest class. Return the narrowest class or narrowest concept C, right? And this C that has A as member, right? So basically we are trying to see whether this holds, right? Now what do we mean by narrowest? So basically it is the minimum atomic concept with respect to this subclass of relation, right? So for example, you observe that A is a member of say person, and A has become a member of say uh, mm, uh, male, right? And you know also that male is a subclass of person. So your output for this particular reasoning task in this case would be male A instead of person A, because male is the more or narrowest concept between this male and person, right? So how do we define it formally? So we are saying that realization of C of A is C with respect to T. So let me put it in a different way. So realization of A is C with respect to T and the A box A if and only if A models with respect to T CA, right, and for all atomic concepts concept D where you have relation like C is a subclass of D, it always holds, right? And in that case, A does not model this BA, right? So basically, you are trying to find this C to be the result of realization of A instead of choosing this D to be the realization of A, because C is more narrower concept than D, right? So these are the kind of 4 tasks that are involved in A box reasoning problem. And let us stop here at this point, and in the next video we will be providing examples, some of the examples that will be illustrating some of the concepts that we have talked about earlier, specifically for the A box reasoning tasks. And then we'll be talking about a very interesting thing, which is the open world assumption and its relationship with the A box reasoning. Thank you very much.